In this video, we're going to be talking about treeps. So a treep is a data structure that combines a tree and a heap, which is why the name is a treep, and it combines a binary search tree specifically and a binary heap specifically. The way that it works is that each node stores two pieces of information. The information that we actually want to store and a random real value. So the piece of information that we actually want to store could be the key along with its value or anything else. And a random real number is exactly that. It's an actual random number. The tree is stored such that the nodes are a binary search tree when you're looking up the information, so that information that you're storing in there is stored based on the rules of a binary search tree. So the left children are less than the node, the right children are greater than the node. The nodes are also kept in order based off of that real random number in terms of binary heap ordering, which we already went through earlier in another video. So you might be asking, well, why are we talking about treeps? Well, it's really interesting to look at a couple of other data structures that are variations of the one that you already know, because then you can kind of see that once you understand one, it's not really that difficult to see a variation of it. So, you already understood binary search trees before this week, and then I just explained to you how min heaps work. Not really that confusing. Once you understand one, there's just like different rules. Then we looked at tries, which are a variation of trees that you've already seen. And now we're seeing treeps, which is like a combination of two that you've already seen. And it's just kind of interesting to see that there are all these different ways and there's pros and cons to using each. So this is an example of a treep data structure. The information that we're storing is these strings. And then the real random values are the numbers that I'm pointing to with the arrows. So those values, as you can kind of see from the picture, follow heap ordering, but this would be considered a max heap, right? So the parent is always greater than its two children, and if you look at every node, that's satisfied. But if you look at the values, those satisfy binary search tree conditions. You can see that cat is less than dick, and dog is greater than. You have puppy, which is less than sloth, etc. So you can see here that the two conditions I described, that the values are sorted by binary search tree ordering, and the random numbers that we're adding in here are satisfying the max heap condition, where parents are always greater than children, greater than or equal to children. So due to probability theory that you'll probably learn about in an algorithms class or somewhere, the height of a treep is log n. And so it's like another way to keep a tree balanced, basically. Insertion, and you don't need to understand probability theory too much to kind of see why this might work. I don't know if any of you thought about this as you started massively inserting stuff into binary search trees, that unless you are choosing randomly to insert things, you're going to very easily build unbalanced trees because, for example, if you add 5, 4, 3, 2, 1, it's going to be really imbalanced. But if you choose those numbers really randomly, chances are, especially if your values are large enough, it is probably going to be more balanced than if you try to come up with them yourself. So that's the first thing. And then insertion and deletion are actually, even though the structure itself seems more complicated, the algorithm and code for insertion and deletion is more straightforward once you can handle how to do tree rotations, which are way more simple than AVL tree rotations. And relinking the nodes is actually a lot more simple than binary search trees. So let's go over insertion. So when you insert into a Treap, the first thing you do is a normal BST insertion. So you just walk the tree using the values and place it in the right place. And then your second step is you bubble the node upwards. That's like the opposite of the sift that we did in the min heap. You bubble the node upwards in the tree, rotating with its parent until its value is smaller than its parent. So an example is easiest to see here. So we're going to add Kitty to this Treap. So you'll see that Kitty should go right here, should go left here, and then should go left here. So that's how you get its spot using just BST insertion. But in order for it to be a valid Treap, this random number is in the wrong spot because it needs to be, parents need to be greater than its children. And so this parent is not greater than this child. So then all you're going to do is bubble Kitty up until that condition is true. So here I can go back. So here Kitty gets swapped with Puppy, Kitty gets swapped with Sloth, and Kitty gets swapped with Ibex, until you have a valid Treap where that condition is now true. And so that is what the insertion process looks like. And so that is, once that swapping algorithm is written, is a really easy thing to kind of implement. Removing from a binary search tree is actually quite difficult because you don't know where in the tree you actually need to remove, and then once you remove it, you have to make sure that the binary search tree is still valid, so you have to decide like which nodes you're going to move up and down. Removing leaves is really easy because they have no children, but removing like the root of this tree would be complicated, right? So you have to do a bunch of checking in order to rearrange the tree to be in the right orientation. Removing from a Treap might seem like it's going to be more difficult because it has all this additional structure, but it's actually not. All you do is you find the node that you're trying to delete, and you keep rotating the node with its larger child until it becomes a leaf, and then you delete it. So let's look at that. So let's say we wanted to remove Kitty. So we're going to keep rotating Kitty through with its larger child. So it's going to rotate with Ibex, it's going to rotate with Sloth, it's going to rotate with Puppy, and then it becomes a leaf node, and then you remove it. And so it has this kind of nice feature with these rotations that makes it really a sort of straightforward algorithm to actually implement. Probably wasn't a straightforward algorithm to come up with, but it's definitely easier to implement. You can actually just write a general bubble down or bubble up algorithm and just call it every time you need to do these operations. As I said, Treaps give a pretty straightforward guarantee that the height of the binary search tree is going to be pretty good and not too large. And so it's expected that Treaps run in log n time because of that. The only expense of Treaps is that bubble up and bubble down process for remove and insert. So they don't provide a particular advantage over a balanced tree or a min heap. I guess they provide the benefit over a heap that they are sorted, so they are better for search than a min or max heap, but otherwise they don't provide any advantage in terms of insertion and deletion. So that's it for Treaps. I hope you guys enjoyed learning about a couple of additional data structures that are variations of the major data structures that we've already talked about.